So in this video, we'll try to solve some problems on rectifiers and basics of diode and the Zener diode as a voltage regulator. So let us take first problem. So this problem reads, a full wave rectifier uses two diodes. The internal resistance of each diode is 20 ohm. The input voltage is 50 volt AC and the load resistance connected is 980 ohm. Calculate the efficiency of the rectifier. Okay. So they have given that the internal resistance of the diode is 20 ohm. The input voltage applied is 50 volt AC and the output is taken at the load resistance, which is equal to 980 ohm. We have to calculate the efficiency of the rectifier. Okay. Solution. So what are the given quantities you write? So forward resistance RF is given, that is taken to be 220 ohm, and load resistance RL is 980 ohm, and input voltage V in is equal to 50 volt. Okay. So this is a full wave rectifier, and we have the expression for efficiency of the full wave rectifier as eta is equal to 8 divided by pi square into RL divided by RF plus RL. Okay. So this is the expression for efficiency of the full wave rectifier when center tap transformer is used. Okay. So let us substitute the values and calculate the efficiency. So it is 8 by pi square, RL is 980 ohm, RF is 20 ohm. So just substitute, and here 980 plus 20, it becomes 1000. Okay. So finally, the simplification of this expression gives you 8 divided by pi square into 0.98. If you use the calculator and if you calculate this, eta is going to be 0.794. Okay. So if you try to calculate the percentage efficiency, so just multiply it by 100 and that will give you 79.4% as the efficiency of the full wave rectifier. So what is the maximum efficiency? It is 81%. Already we have discussed it in one of the previous video. Okay. So this is how you can calculate the efficiency of the rectifier. Okay. Similarly, the half wave rectifier is having the efficiency 4 divided by pi square into RL divided by RF plus RL. Okay. Instead of the factor 8, the factor 4 will appear in the expression of efficiency of the half wave rectifier. Okay. By the similar way, you can calculate the efficiency of the This problem is on the semiconductor diode. A semiconductor diode is forward biased using a battery. A change in input voltage by 0.8 volt causes the change in forward current by 10 milliampere. Calculate the forward resistance of the diode. Okay. So here the diode is forward biased and there is a change in input voltage by 0.8 volt. Okay. Then it is observed that the forward current will change by 10 milliampere. Okay. So you have to calculate the forward resistance of the diode. Solution. What are the given quantities? Let us take delta VF as the change in forward voltage 0.8 volt and change in current, forward current is delta IF, that is 10 milliampere. Okay. So if you express milliampere in ampere, that will be 10 into 10 to the power minus 3 ampere. So we have to calculate what is the forward resistance of the diode. We have RF is equal to delta VF divided by delta IF. That is voltage divided by current, that is in accordance with the Ohm's law. Change in input voltage divided by change in the forward current. So substitute the given quantities. It will be 0.8 volt divided by 10 into 10 to the power minus 3. Okay. If you simplify it, you will get 0.08 into 10 to the power plus 3. Okay. If you take it to the numerator, it will become 10 to the power plus 3. And final simplification gives you the forward resistance RF is equal to 80 ohm. Okay, so this is purely based on the Ohm's law. So this is about the forward resistance of the semiconductor diode. This is the second problem. Let us take the third problem, that is on the Zener diode. So here, for the circuit shown below, find the output voltage, the load current, and the voltage drop across the series resistance. Okay. In this question, the circuit is given, and in the circuit, we have to calculate the output voltage that is taken across this load, and the load current IL you have to calculate, and the voltage drop across this series resistance. What is the voltage drop here? You have to calculate. So this is the circuit containing the Zener diode. This is the Zener diode, and this circuit is the voltage regulator circuit. Okay. So these three things you have to calculate. So look at the circuit. So here input voltage is 120 volt and series resistance connected is 2 kilo ohm. Okay. Then the Zener voltage Vz is 50 volt, and this total current will divide into two parts, load current and Zener current. And the load connected is 10 kilo ohm. Okay. Solution. What are the given quantities you write? Vz, that is Zener voltage is given 50 volt. The load resistance RL is given, that is 10 kilo ohm. The series resistance R is given. This is the series resistance, that is 2 kilo ohm. And input voltage V in is given, that is 120 volt. So what are the asked quantities? You have to calculate what is the output voltage, what is the load current IL, and what is the voltage drop across the series resistance, that is taken to be VR. Okay. So first you have to identify whether this Zener diode is in on state or off state. Suppose this input voltage is greater than Vz, then it will be in on state, and this output voltage will be always equal to this Vz. Otherwise, there is no Zener current. This Zener diode will be in off state if V in is less than Vz. So here clearly input voltage is greater than Vz, that is 120 volt, where Vz is 50 volt. That's why in the circuit V in is greater than Vz. Therefore, Zener diode is in on state. Therefore, the output voltage V naught will be is equal to Vz. Okay. So therefore, V naught will be is equal to 50 volt. That is the output voltage. That is the first question. Second question is the calculation of the load current. So load current IL will be is equal to this voltage across this load resistance divided by resistance. That is in accordance with Ohm's law. IL will be is equal to V naught by RL. So V naught by RL. So what is V naught here? Sorry. V naught is 50 volt and RL is 10 kilo ohm. There's 10 into 10 to the power plus 3. So if you simplify it, it will be 5 into 10 to the power minus 3 ampere. Okay. So minus 3 ampere means it is milliampere. So load current will be 5 milliampere. That is the value of load current. So next, third one, you have to calculate what is the voltage drop across the series resistance. Okay. And that is given by VR is equal to input voltage minus output voltage. So whatever the input you are given and what is the output taken, the remaining voltage will drop across that series resistance. So what is the input voltage here? It is 120 volt. What is the output voltage? It is 50 volt. So 120 minus 50, it is 70 volt. That is the voltage drop across the series resistance. Okay. So this is the another one problem on Zener diode as a voltage regulator. Let us take fourth problem. That is again on the Zener diode as a voltage regulator. So here in a voltage regulator circuit containing the Zener diode, Vz is equal to 60 volt. The input voltage is 100 volt and the series resistance connected is 5 kilo ohm. The output voltage is taken across the parallel resistance RL, which is equal to 10 kilo ohm, which is parallel to the Zener diode. Okay. So this is the exactly similar circuit shown in the problem number 3, where VZ is 60 volt, Zener voltage is 60 volt, input voltage is 100 volt, the series resistance is 5 kilo ohm, and the load resistance is 10 kilo ohm. What are the quantities you have to calculate? Find load current, Zener current, and total current in the circuit. Okay. Already I have shown you in problem number 3, total current will divide into two parts. One is load current along load and Zener current along the through the Zener diode. Okay, let us calculate one by one. What are the given quantities you write? VZ equal to 60 volt, Vin is equal to 100 volt, series resistance R is equal to 5 kilo ohm, load resistance RL is equal to 10 kilo ohm. And you have to calculate the load current IL, Zener current IZ, and the total current I. So let us calculate. First, identify whether the Zener diode is in on state or off state. Now clearly V in is greater than Vz because V in is 100 volt, Vz is 60 volt. Therefore, Zener diode is in on state. Therefore, V naught is equal to the Zener diode Vz, and that is equal to 60 volt. That is the output voltage. Okay. So once you calculate the output voltage, you can calculate the load current. And load current is given by IL is equal to V naught divided by RL. So therefore, you substitute the value of V naught, that is 60 volt. What is the load resistance? That is 10 kilo ohm. So 10 into 10 to the power 3 ohm. So if you calculate this, it will be 6 into 10 to the power minus 3 ampere, or it is 6 milliampere. That is the load current flowing through the load resistance. Next, the total current you can calculate, that is given by I is equal to input voltage minus output voltage divided by the series resistance. So basically, this will give you voltage drop across the series resistance. Voltage drop divided by resistance gives you the current. So substitute, input voltage is 100 volt, output voltage is 60 volt, and load resistance, that is, sorry, not load resistance, series resistance is 5 kilo ohm. So just you substitute, it will be 40 by 5 into 10 to the power plus 3. So 40 by 5 is 8 into 10 to the power minus 3 ampere. So minus 3 ampere means, sorry, 10 to the power minus 3 ampere means milliampere. So load, the total current is observed to be 8 milliampere. Okay. So finally, you calculate the Zener current, and Zener current is given by IZ is equal to I minus IL. So that is 8 milliampere minus 6 milliampere. So it will be 2 milliampere. Basically, this total current will be is equal to IL plus IZ. So therefore, IZ will be is equal to total current minus load current. So that will give you the Zener current as 2 milliampere. Okay, so this is another problem on Zener diode as a voltage regulator. So in the description part of this video, you can find the PDF file containing these problems. Okay, you can make use of this for your reference.